Look at this, okay? And you're going to find it, well, let's see, I think this thing appears on page 338 is the idea. And now watch what happens here, because it gets a little tricky. And what I'd like to see, that some of you can work this problem almost in your head. Most of you will not. Okay? But some people will. So here's what I have. We have this little thing, d dx of f of, no, I don't have an f here, I have the function itself. Cosine.
What page is
338. First part of the derivative. The first part of the fundamental theorem of the calculus, I should say. First one there. Okay? Now, you see this, and most of you can just write the answer down. Okay? Oh, I don't have everything finished yet. Here's A and here's X. Now, in a few minutes, when I do the fundamental theorem of the calculus again, when we have a function going, oops, why don't I'm not going to quite do this one. But this is the way this function goes if this is nothing more than the cosine of t. I got 2 t squared here, so that varies some things. It changes things. But now, in this case, I'm going to start here, and I'm going to run to some point over here, x. And this could be a, and now this is defined in terms of that. Now, we're just going to look at this a minute. Okay? Now, who can give me the answer to this, what this is?
Cosine x squared dx.
Oopsie. This. This is all it is. That's just it. Okay? Now, you have to realize you're going to start from some point A, and we're going to land up with x. Now I'm going to change that just a little bit. We're going to go this way, d dx of a to the x squared cosine t squared dt. Okay? Now, this is not near as easy. We're not running to x. We're going to run to x squared. We're not running here. We're going to go that, whatever that's there, squared. So we're going to be further out. Okay, now what is this going to be equal to? This, I'm going to tell you first, is going to be equal to dy dx. Now, when I do that, you notice the notation that we've done in the past. This whole section right here is y. I'll just write that over here. Y is equal to the, let's see what I want here. I want all this stuff here. X squared cosine t squared dt. This is the y right over here. So you see this over here? Okay, now, the next thing I'm going to do is, I would like this not to go to a square, to something else, so it's going to be called substitution. And we're going to spend a fair amount of time with substitution, but here's a nice little place for it. And so I'm going to say u is going to be equal to x squared. I'm going to leave that there for just a moment, and I have to do some more work with it. Okay? Now, when I do that, I'm over here. And so what I'm going to do is try to put a u here. I'm going to put a u here, so I want a u here also. I have a u here, I want a u here. And I can't just put one there. I have to make certain I'm doing things that are equal. So what I'm going to do is this. I'm going to take this dy dx and make that dy du times du dx. Now that's kind of clever. Cancel these two out. Can you get this? Any questions about this? Okay. Now, so I have this. I'm going to do this next, and I'm going to write this d. Now, and I'm writing this term. I'm going to put a du, and now I'm going to put y in. Like I showed you over here, that's this. Only I'm going to put the y with a u up here. So I'm going to go like this, from a to u, cosine t squared dt. Okay, now that's just this term right here. Now behind this, I have to put, we'll put this like here, I have to have du dx. Now, questions on that? Okay, now, what in the world is this? Well, that's over here. I'm going to take the derivative of this, and that's du I'm going to write it this way. I'm going to take the derivative of that, and then this is going to be 2x dx. And I'm going to put the dx down here, like this. Are you with me on that? Any questions? Okay, so this is over here. So now, I'm going to do this first. Grant, you told me a while ago up here something that was there. What is this quantity right down here?
That would be just cosine x squared. Or u squared, I guess.
Oh yeah, okay, very good. He says it's going to be cosine, and it's nice that you made that first mistake because that helps us a little bit. See, it's supposed to be u squared because this was an x up there a while ago, so that's there. And so that's there. That's this whole part here. And this part behind here is nothing more than a 2x.
Can you move the thing up, please?
Yep.
Yeah.
Okay, see that? Now, this is equal to the cosine. Instead of u squared, I'll go back here and resubstitute this back in, which would be x to the 4th times 2x. That's my answer. Okay, you've got two problems to do like this. And I would like to see if some of you can just write the answer down. After working one, maybe the second one you can. If you can't, no big deal. You can just do it this way. So, yes?
What is that telling us then?
This is telling me that way back here, when I do, these are inverses of each other. The derivative and integral of this quantity over here is this. Now that's a chain rule working in reverse because of this thing here that gives you the chain rule effect in the inside. Okay, now for some of you who are kind of rolling along here, this is what I really want to see. But at this point, some of you could say, oh, I see what's happening here. This is cosine, and this is going to be, instead of just going to x, it's going to go to x squared, so this is going to be x to the 4th. Because this is squared, x squared, x squared, x squared squared. So that's to the 4th. And then I have the derivative here, like that, okay? For chain rule kind of effect. And so, I don't know if you can go there, but otherwise, do these couple of problems. This is the first half of the fundamental theorem of the calculus, okay? We don't use it very often, not very often, but it's there, and this author does a little bit of it. I had another author before this one that I taught that did it even more. Yes?
Okay, so on the bottom line you have cosine u squared.
This is where we are?
Yeah, and then like the 2x, did you get the 2x because of the chain rule?
No. The chain rule is right here.
Okay, yeah.
That's the chain rule. Okay? And see,
Did you take the derivative of u?
yes, I took the derivative of u up here. Okay? Okay? So, and hey, if we need some more time on this on Friday, no problem with it. But a dandy little test question, and I wouldn't do the easy one, which we used actually in here. Yes?
So, for the test, can we just write the answer?
No.
Or we're gonna have to do all that?
Do this. So you know what you're doing. Okay? Okay. Now, do we have any extra problems to do besides those that are up there in terms of review?
57.
On what page, Grant?
The other assignment. 345. 345.
Okay, 345. And which one?
57. I just
50.
I don't know.
Oh,
It
okay.
was not clicking.
Yeah. That's nice one. Okay, this means the next, this is going to be page 345, you said?
Yeah.
And it was 47?
57.
57. Okay, any others in that group? Anything out there that we have to do?
23 then.
23 in that group too. Okay, let's get that taken care of then as we're going along. Okay, the first one is number 9, number 6 up there on page 252, number 6. Kind of a cool little question, page 331. Okay, and he says use geometry to do this from 0 to a, and here's x dx. Okay, now, we're just going to use geometry now. And the idea is here, so you guys get an idea that this has
It's
a
number
geometric.
6.
Pardon?
Number 6, not number 9.
Yeah. 6 is the epsilon or whatever thing.
Oh, just a second. Did I copy that wrong?
Yeah. We did. We need to do
Well, I copied it wrong up there. You wanted 9. You wanted 9. Okay? So, sorry about that. Okay, now, here's the function that runs this way. That is f at x equals x.
Right.
See that? Okay, now we're going to go from here, 0 to a. Okay, and this is a. And this represents area at this point. Okay, that's area here above the x-axis. And this is a, this is a. So this is a squared over 2, and we're done. With geometry. That's the area of this thing right here. Okay? Now, this isn't in this problem. But this is where we are today in terms of what we've learned. This is what the fundamental theorem of calculus says. I'll take the antiderivative of this, which is x squared over 2, right?
Right.
And then I'm going to evaluate it from 0 to a.
Right.
And that gives me a squared over 2 minus 0. Question on that?
Yeah, I have a, why do you put the line there and then 0 to a? What's that?
Okay, this means we are integrating this section over here from the bottom, which is going to be negative, and this is on top over here. And we want to take a little more look at that as we're going along. I might try and do a little more of it today. Starting, well, no, we're just doing it from A to B. This is the symbol form that we use. Pretty universal. Okay? The next question up there is 39B. Please look at that, because some people had some difficulty. There are a couple tricky little things in that one. Okay? On 39, you notice what is defined to be 32. See that? That's in the reading. That's equal to 32. Okay? Now we're given this. And I would like to do some work with this thing to show that I can get it in the form that we have. Okay, now, in the book, it has a 3 over here. Okay, so I'll put a 3 here, and I'll put a 1/3 out in front. Any questions about what I just did?
Yeah.
Okay, we know with integration that any constants here could be put out here. A constant times a derivative is a derivative of that constant in the function. So if I take 1/3 now put it back in here, 1/3 times 3 is 1, 1 times anything doesn't change it. Okay? Okay, now, the other thing you'll notice that this is in the wrong order. The book has 4 minus x. So I can make this 4 minus x by just doing, I'll do different color. I could do it this way, put a minus here, a plus here, and a minus out here, right? You with me? Now this is 4 minus x. But I don't want this minus here. I'm going to dump it out here. Pardon?
Why did you have to make it a negative 3x though?
Because the negative times the negative is a positive. Okay? Now I'll give you another one. We had this. Now watch what this is. If I take a negative 1 times a negative 1 times x minus 4, I still have the same thing. So here it gives me a negative 1, and now I'll distribute this over here, which gives me a negative x plus 4. See, now they're the same. And this could also be written as a negative, the quantity 4 minus x.
Yeah, but it's a positive. Out front. Are you looking at A, I guess?
No, I'm looking at B. I'm looking at B.
Why are you over 3 in front then?
Yeah.
Here's I got a 1/3 over here. Okay? Now, here's another one. All of this stuff we've done before. You know from way back, if you had 4 minus 1, you get the opposite of 1 minus 4, right?
Yeah.
So if you do like this, they're going to be equal, right? Okay, so we really don't have to go through all this if you know your arithmetic. Okay, now, I don't want this negative over here. I want it out here instead, so I just moved it. Now, how much is this quantity right here?
32.
It's exactly like this.
Okay.
So my answer is a negative 32 over 3. Questions on that? Clear as can be? Nice little things. Okay, now I'm going to go to 43, and we've got something very similar working there. And these are kind of nice problems to get acquainted with what integrals will do. 43, it tells you what equals 3 over 4. Okay, minus 3 over 4. See that thing? Now, the question is 43, probably both of them. Okay, the first one. Notice what we have there. We've got, well, let me just take that, just write it here a minute so you can see it. From 1 to here. And it's a mess all the way. 2x cubed dx. Okay? Now, you'll notice the other one, I better write this over here so you can see it quite quickly. That I think he has here x cubed minus 2x dx like this. Now notice, there's a 2 here, too much. See, this doesn't have a 2 in front, so what I'm going to take out of here is this. I'm going to factor a negative 2 out of there. So I'm taking a negative 2 out of there, still like this. And when I take a negative 2 out of here, I'm going to take this one first, write that this way, and this is going to be minus 2x. Are you with me at this point, what I did?
Shouldn't you take an x out?
No, I don't want to take x out. I could have, but for all practical purposes, this is what I have to give. I'm giving.
Oh yeah. Okay.
See, so now I'm going to take this out of here and put it out the front. This quantity right here that I have in the box is a negative 3/2 times a negative 2. Okay? Now, the second part, does anybody need any help with that one? You notice we go from 1 to 0 instead of the other way. Instead of integrating from the left to the right, we're doing from right to the left. And so we have to shift it. Any questions about that?
So then isn't it just it would be a positive, but it's a negative because of that it flipped?
Will you listen to Brianna, please? And I would like to comment with what she says, because there's a couple things in here that you need to notice. We're actually doing 2 negatives. What did you say, Brianna?
I said it goes to a positive, but then it goes to a negative because the inside is split.
Yes. Did you hear that? She said 2 negative things. One is we're going in the other direction here, and the stuff in the inside is negative. So you have a negative, negative, so that answer is just going to be
positive.
Yes, but it's the thing is it's a negative 3/4 to start with. Okay? So we got that one finished. 61. 61. Okay, now.
Mr. Kramer,
Yeah.
I computed 43A wrong. You got 3. You wrote negative 3/2.
Yeah, he wrote 3 halves.
Oh, okay. Never mind.
Okay.
I knew you were right.
Thank you for taking care of it. Okay, now the next one. This is what we'll do basically with Riemann sums. And I think you can do a lot of this in your head rather than doing this mechanical stuff. And how do you get your calculator ready to handle this problem? Okay, so what we're going to do is we're going to go from 1 to 4, and we're going to have 2 square root of x dx. Now, we're saying that we're going to solve this thing with Riemann sums. Now, I'll put something on the board in just a minute about that too. Okay, and so in our calculator, we have the sum of the sequence. Okay, and in the sequence, we're going to put what here?
2 right left.
And then we put the x, and now the fun begins. Okay, we have a distance of 3, and we're going to break it into how many parts? All equal.
50.
We're going to put 50 of them, right? So how wide is any one of them?
6.
3 over 50, which is 6 over 100, which is equal to 0.06. Correct?
Yep.
Okay, now, I told you, when we were doing this problem, we were going from what spot? The middle. There's a middle for a reason, because it makes things a little more interesting. Okay, so where do I start from? 1 point what? 1.03. And where do I end?
3.97.
Now, some of these people who are responding were in my class this morning before school, so don't get too excited if they just really know the answer, okay? Anybody has a question about that? Okay, now, how do I go from one step to the next? Okay, now, up to this point, what I have done is I've taken all of these sums, these are the heights, I've added them all together, and then I have to get the widths. And the width is 0.06, like this. Okay? I wanted you to be able to do that pretty quickly. That's why I assigned that one the way I did. Any questions? Okay. There's one other one up there, 69. Okay, that's a geometry problem. Nothing more than a geometry problem. And it says this. I have y equals 1 minus the absolute value x, like this. Okay, let me take you back to Algebra 2. And I'm going to show you a family of functions. What does y sub 1 equal the absolute value of x look like? Well, that's this curve, like this. It goes this way and this way. Okay? But now what happens here? This one's upside down, and it's raised 1. So this is what we have. Okay? We have a function that goes like this. With me? Now, in terms of integrals, so you know what we're doing, I'm going to take the integral of that, and we're going to start here at a minus 2, and we're going to go up to 2. See that? So now I'm talking about this area right here, and this right over here. This, where we're talking about that area, from here to here, that's a negative number. From here to here is a positive number. Here to here is a negative number. Okay? Now, this is 1 up, and this is 1 over, and this is a minus 1. And so what's this area? That area is 1. Lots of 1s going. What's the area of this? Just a second. This is 2, and so this is going to bring me to 1. And so this is 1 this way, 1 this way. So that's going to be, if we're doing Riemann sums, it's a negative 1/2. If we're doing area, it's a half. With me? Area is a half, but if we're doing Riemann sums, it's a negative half. Same story goes over here. That's also a minus 1/2. So if we go to net areas kind of idea, we have nothing here. That's a 0. Okay? Now, I will just also do a couple other things here because we're moving very, very rapidly today. Page 345, number 23. 23. I like 24 better. May I do that? I think, Grant, you're the person who asked.
Yeah, you can do 24.
Okay. Now, because you see, 23, it's just you do the work very nicely and say, okay, does it look like? And I think what we have to have there, the answer is it close to 2?
Yeah,
2 1/3. Okay. And if you look at that area, it's 1 unit long and 3 high, but that'd be too much because some of it's cut out of there. So it looks like about 2. What does 24 look like? Like nothing, right? Should be a 0. So now watch this. This will be just good practice for using the fundamental theorem of the calculus to do this one. And we do sine x plus. Now you can do this problem wrong and still get the right answer. So be careful. And I will notice that. Okay? Now, in this case, what's the antiderivative of the sine of x?
Negative cosine.
Oh, you're good. Negative cosine of x. Okay? And what's the antiderivative of that?
Sine of x.
Okay, now, and a while ago Grant asked, about putting this in here. And then this is 7 pi over 4. And now this gets a little tricky. This is, all of these values, this should be a 4. All of these values put in here are going to be some kind of square root of 2 over 2's. Okay, that all of them are going to be either positive or negative. Okay, to get that, the cosine function goes this way. That's the cosine, and the sine function goes this way. And let's see. I'll do this. Okay, now I think that's all I need, and I can do it from there with what I have. Okay, now when I go to 7. We're doing the blue one now. 7 over here, so I'm going to be way out here. Oh, just a second. Got to think that through a minute.
It's a negative cosine.
Would you say it once again?
It's a negative cosine.
Yeah. Okay. I'm going to first figure out the value of this at this point. Okay. Yeah. That's good. That would have confused my mind. So, but if you can handle that, go ahead. Okay, now I'm just going to do this, just the cosine over here, and so this is going to turn out to be the square root of 2 over 2?
Negative.
A negative, because,
no, it's a positive because it normally is a negative.
Okay.
Yeah.
I might have to back up, but I think this is what it is. Okay, now what is this one? When I'm way out here. Okay, that's going to be a negative square root of 2 over 2. Ooh, am I doing this right?
Well, is it going to be 0?
Pardon?
Is it going to be 0?
Yeah, it's going to be 0.
Question.
Yes.
Can you do it graphing a circle too? That circle
Sure.
graph? Yeah, so wouldn't x be a positive number and then you stick the negative in front of it?
Okay, you said doing it this way.
Yeah.
Okay, now we're doing this one first?
Yeah.
Okay.
And you're at 7
That's
pi,
right
so you're
and
in
left.
quadrant 4.
Okay, and this is going to be quadrant 4.
Yeah, so
we're going
x
to be
is
right
positive.
over here.
So it's a minus square root of 2 over 2. It's not a positive. Because your cosines.
This is what you're telling me.
Yeah, okay. And it's a positive sign.
Okay, you know, notice what DeVries did. Now, he went this way. This should have been a negative square root of 2 over 2. And this is square root of 2. And now I have to take this quantity here, negative that whole business that comes. Now, when I put this here, I happen to be at the same spot, don't I? Instead of going around this way, I come back this way. So this is going to be a negative square root of 2 over 2. And the same story is going to go over here, which is another square root of 2 over 2. Now look at all what we have here, which turns out to be 0.
What number is
that? 24. 24.
So you can just use a circle too in your head. Because that's easier.
Did you hear what he said? Now that I did it, I would prefer to go that circle too.
Okay.
I like it better. But whatever, and if you really get desperate, you've got a calculator and you have a blue sheet. Okay? And I was going to try to do without a blue sheet today. Derek, thanks for pointing that circle out because it really works a lot better in this particular problem. Okay, now the next one we want to do is...
Can you add one more onto that list real quick, Mr.
Oh, sure.
25 or 26, one of those two.
Can you do 25?
Okay, here we go, 25. I like it. This is just really... Okay, I'm going to try to teach you something... not yet. This one doesn't turn out to be nice. Okay, we have minus the quantity x minus 1. Now notice I changed this around the direction. May I do that? No? Okay, you don't like that. Very good. 1 minus x, so you can do it the hard way. You want to multiply this out, so it's going to be a negative x squared, right? Plus 5x, is that right? And the last is going to be minus 4?
No, it's not plus.
It's not 5.
Yes, it is. Okay?
But, oh, it's a negative.
Okay?
Yeah.
So negative x squared plus 5x minus 4 dx. Like that. What's the antiderivative of that? Correct? No. This way. With me? What's this one? Are you with me?
Yeah.
and minus 4x like this, and now I'm going to evaluate this whole thing from 1 to 4. Okay, so this is going to be negative 64 over 3 plus 80 over 2, okay, minus 16, minus the quantity. Now, hey, this is where I usually put a minus here so I don't get signs wrong too often. This is minus a third, plus 5 halves, minus 4. Okay? Now, this happens to be 40. And so, as I'm going along here, I'm going to make this a negative 64 over 3. And then I'm going to write this term. Okay? And that's going to be plus a third, because I got both thirds here. See that? And then 40 minus 16 is going to be a plus 24. And then this is minus 5 halves. And this is plus 4. With me? Okay. This here turns out to be how many thirds? Negative 63, which is a negative 21, isn't it? Because this is negative 63 over 3. That's a negative 21. And I'll leave this one be for a moment. Plus 24, minus, plus 4. No, this is out of here already. Now I'll put this one last. Okay, now I can do this pretty quickly. This gives me 7 minus 2.5, which equals 4.5. Okay?
Very nice.
Now, one of these days I should show you how in your TI-84s you can just do this in your calculator to check your answer. Okay?
That's nice.
Now, we also have a question on number 340, or on page 347, number 57. 57. And that's one of those matching ones again. And see if you have any questions about that. The first one, it says A, what function is the area? The bottom ones are the capital A, capital B, capital C, capital D. And you'll notice that A is associated with C. Okay? How? Look at here. When I figure out this area, like this, and this is the area this way, and we're going this way, if I have it here, and it just keeps growing, linearly.
Oh,
Okay? So the area is going to be going this way.
Okay.
Okay? Now, the next one, we're going to go to B next. Now, notice what happens. The area is going to grow, and by the time we get to B, there's only going to be about nothing. Okay? And so, in this case, the area grows until we get where it intersects the x-axis. And then it starts shrinking until we get to B, where there's probably nothing again. And so that's like D.
D?
B. Just a second. B, like the B one. Yeah, like B. Okay?
So B with B.
Yes, B is B. Okay? Then we go to the C part, and we keep growing all the time. And there are two different rates. Okay, we're looking at this. We have this like this. Okay? Now, all the way up to here, we're growing. But at this point, we keep growing at a faster rate, and then we start slowing down. So we're going to see a rate change like this, and then we're going to look at it, the rates changing like that.
D.
So that's going to be like D.
Yep.
Okay? And then the D is like A.
How do you figure that one?
Okay, now that one is a given. That's one you should just get immediately, because you notice you're talking about D, you start below the x-axis.
So your sine curve,
Yeah, hey, that's, yeah, a negative sine curve. Good. And you're starting going down, so you better be negative.
Gotcha.
Okay?
Makes sense.
Okay, now, the only thing I have left to do today is to go through the fundamental theorem of the calculus once again. Here we go. I'll get rid of all of this stuff. And Okay. As we get started, I'm going to put a few things on the board that we're going to are resources for us. And the first one is this: review of at the beginning of the book, and we have this. If I go to the limit as h approaches 0 of a at x plus h minus this here, all over h, that's equal to what?
A times x.
Okay? That's old stuff. Okay? And we're going to use that today. We also did this. We went an integral like this, f of x dx is equal to what? We said that's going to be f of x plus a constant, provided that f prime of x equals f of x. Question on that? Okay. The next one I'd like to do is tie Riemann sums into area. And this is on page 324. And it's kind of nice to go to that page so you see what we're doing and see if there's anything there I want to say when I'm looking at it. I think I have the right page. 324. Yes, okay. You see that the integral is defined to be a Riemann sum. Okay, so we have an a here, a b here, an f of x dx. That's equal to the limit. Now I'm going to write it differently in the book. Not much, just a little. I'm going to go. Okay, are you clear with what we have here?
No.
Okay, now, yesterday, my algebra 2 kids, we used x bar for the first time, which was a mean. Here it doesn't mean the mean. It just means some point within the kth interval. And I think Trevor was one that asked a question a few days ago about where that interval is. And we're going to pick up we're going to take an infinite number of them here, that's what's here. But this and this is very much like we did a little while ago in terms of that 2 times the square root of x with our calculators. That's this, okay? Now we've got that, okay? So, this tells me that this could be kind of interesting stuff if we learn how to work with it. Okay? And that's what we're going to try to finish up doing today. Well, we've been using it a little while already, but why does it work? Okay? The next thing I'm going to do is I think I'm going to go to page 335, and that's another neat little thing dealing with area. 335, oops, see how we're on page there. That's the area at the bottom of the page there. And notice what it says. It says area at x. And I'm going to draw you a picture so you get an idea what we're talking about here. We're going to pick up our interval like this. And we're going to start here, and that's going to be a. And over here we're going to have an x. And this is a t. This is a t-axis. This is f of t, like that. And this is the area we're talking about here. That's the area we're talking about, and that's going to be a little x there. We're going to need that in just a few minutes. Okay, so this we say is going to be equal to a to x of f of t dt. Okay? Now, with this one, we've been doing a little playing. We started the class period with putting a dx in front of it. Okay? Okay, that's fundamental stuff to start with. Okay? Now, let me just put a couple of little things here before I get to the overhead. We have got, this is what we're looking for. This is an integral from a to b of f of x, ooh, okay, I'm okay, dx, and we'd like it to say this. Okay? That's what we'd like it to say. And if we can, we have got a gem of a tool to use. And we've seen that it does work and all that kind of stuff. Okay, so I'm going to start with this. And I can't put here directly. There are two parts. And so what I'm going to show you, the two parts of the fundamental theorem of the calculus, and using this stuff over here. So here we go. And it will go fairly fast, I think, today. Okay, now, the other day when I did it, I had a zillion questions.
Yeah.
And so I had to go back and forth. I don't think I'll have as many today, but I'll try to answer them as we're going along. Okay.
Can you move
well, let's go now to page 338. And it says Fundamental Theorem of the Calculus, Part 1. So we're going to do Part 1. And as you're reading along there, what I'd like to prove is that a prime of x equals f of x. Okay? You see that thing down there? And so here we go. I've got to start with a picture. And I'll make it just a little bit different than what I did yesterday, but not much, or the other day. We'll go this way. Okay, now we're going to start at A. And over here, I'm going to put an X. Now, with what I have there, notice the bottom one. This area right here is A at X. By my definition of stuff. See that? Okay. Now, what I'm going to do next is go over to the little ways. And this little area here is going to function in a sense like a Riemann sum. Okay? And this length is h, and this is x plus h. And this is a t, and this is an f of t. Any questions? Okay? Here we go. We've got all this together, and now I'm going to take this area, running all the way from here to here. That area. Okay? That area is going to be defined as A at x plus h. That's the red. I'm going to subtract the area of A of x. Okay? I'm going to subtract this away from all of this, and then I'm going to land up with about this. Now watch what I'm going to do next in terms of getting that area. That's going to be approximately, which is lousy stuff, but we're going to use it, f at x times what?
F h.
Okay, this height. Okay? Now that would be this height right over here times this width. Okay? Now, the first part, what I'm going to do is I'm going to divide both sides by h. So I'll do this by h like this, and this by h. And then I'm going to take the limit of that. Okay? And I'll rewrite that. So I'm going to go to the limit as h approaches 0. So the trick is squeeze all the life out of that thing without getting to 0. Because if I'm 0, I'm in trouble. Okay? And then I have this. And you'll notice something else I have on the board. Minus a at x all over h. I have this. But I know what that is. Bingo! It is a prime of x. Okay. So I at least have this. Now, can I do something else to show that this is equal to something different? It is equal to this, but is it probably equal to something else? So I will go back and do a little different procedure. I'm going to start again with this. A at x plus h minus a at x. And I have that. And what I'm going to do is this. I'm going to break this little area up into this height. And this is going to be m, little m. And this height over here. I should have put the little m over here. That's a little m over there. See that? That's this height right here. And this is the maximum height in that interval. Okay? That's why I drew it that way. So this area right here is going to be less than or equal to that big M times h, and on this side it's going to be less than, which is the least part, which is a little m times h. Are you with me? Okay, now the thing goes really fast. Again, I'm going to divide everything by h. It's interesting how this one goes similar to that one. Okay, now, so these h's are out of here. And now I'm not going to go this direction. I'm doing something else here. I'm going to do this. I'm going to take the limit of this. And so I have the limit as h approaches 0 of little m. Oh, what's that going to look like in a minute? We'll analyze it. Is less than or equal to the limit as h approaches 0 of a at x plus h minus a at x all over h is less than or equal to the limit as h approaches 0 of big M.
Whoa.
Okay, now, what is this equal to? We can figure out what that equals, because when we squeeze this all the way in here, it's going to be turning into just this. So this is going to be an f at x. Now I'm going to do the other side for the maximum. Get the same thing there. So now I'm saying we have here this, like this, of ax plus h. Can you still see it on the board all right? Over here, like this. Okay? Now that is saying that this quantity is equal to this. In other words, this quantity right up here is equal to f at x. Therefore, we have this, and I've got this done. Okay? Now, before your eyes, a miracle just happened. I don't know if you caught it. We were working inside here with like this, and we were working with an integral, and all of a sudden we saw that this f at x dx on the inside turned into an a at x on the outside. This here turned into an a. Okay? Now, we're still not home free. We've got that much done, but you'll notice what I have up here. This is not an a, and that is not an a. I got an a on this side. Okay? So now I got to do the other part, which is really cool, and it's really simple. Okay? Now that happens on page 339. See the top of the page? The fundamental theorem of the calculus, like that. And here we go. This is going to be very quick, I think. What do we have? I have this here of f at x dx. We're going to go to a to x, I think, or we can do it that way, whatever. No, we'll just go to a to b. That is equal to a at b, really. We just finished doing that. Okay? Are you with me on that? We just finished doing that. Okay, now, going back a little bit, we know this part. This here, f at x like this, dx, is defined to be equal to, and that's why we have the c's, and after we have the c's done today, we never have to worry about c's again, okay? And this is going to be f at x plus c, when f prime at x equals f at x, okay? So we have this. Are you with me? So, here we go. I've got this. Are you with me? Because if you're not with me now, I want to get you because the rest goes really fast. Okay, now, this here says a at b is equal to f at b plus what? A constant. You with me? Okay, and we're going to say f at a is equal to f at a plus a constant. Okay? Now, watch what happens here. How much is f at a equal to? I don't have a picture. And see, it's right here. Right here. It's right down here. It's nothing. We're right here. We've just got this little line. Okay, so that's equal to 0. Okay, that's equal to 0. Okay, so we'll do that in a minute. Now, look what happens up here. A at b. Now, a at b is equal to this quantity, right? We proved that. We got that all done.
Yeah.
But now, is this going to be equal to, there's the big question, is this going to be equal to f at b minus f at a? lo and behold, it does, because look at here. Here's f of b minus a f at a, like this, and this is still equal to this, right? Oh, let's just take this out of here. This is equal to, let's do it on the side. This is a at b, okay? Which is that area we're talking about. Now that's equal to this, which is f at b plus c minus f at a quantity plus c, okay? And therefore we got f of b minus f at a. Okay, now, just a second. I think I have something in my... Okay. See, and this is why that author by the name of Stewart says things like this. It ranks, this fundamental theorem ranks as one of the greatest accomplishments of the human mind. Okay? And you guys were able to understand much of it. And I'm really happy that you could. I could have just given you the mechanics. I could also show you very quickly how to do it with your calculators. That's all pretty easy. But you got to see how it's really made, and therefore, I would hope, take more ownership. Not as a trick, but as something that's really quite amazing. Okay, now, a while ago, I talked to you about Euclid and his geometry and his logic. Okay? That's 300 years before Christ. We go from then, which deals with Archimedes, Eratosthenes, Aristarchus, all of these great mathematicians, these are all about 300 BC. Plato and Euclid, Plato and Aristotle in that period too. We go all the way for about 2,000 years until we get another great big thing right here. And this is, of course, what we're talking about here. These other guys were just tremendous, and now we have this explosion that happens in the 1600s. Okay? I have questions. Anybody have a question? Can you believe it? We're finished, and
Can we go
De Vries. I suppose you've got that done already.
I just finished.
Okay. Now, I have time for questions. Yes.
Can you help me get started on 53?
Okay. We're going to be a little more informal the rest of the period. You guys have worked, I would think, fairly hard. This last period, I think we were fairly focused. And so, if you need a rest, whatever. You said 53?
Yes. Going there.
Get it, dear.
Yeah,
Get it.
Dear Bear.
You do?
That's
you just say
Tanner, I think these are the hardest part of this section. Now, I'm going to write it a little bit differently in the book,
What do you
Dan.
mean? You don't say that.
No, you just
Okay.
plug in X,
You with me?
XP
Yeah.
and take
Okay, now,
X to the
you notice
X.
we are running from an A somewhere, which is a 2. That's no problem. Okay? So that's not an issue. This is the issue.
Yeah.
So immediately, I would like to make that, instead of a square, just a regular number, and so it's going to be called U substitution. Okay? Now, so what I'm going to do next is, I'll just take the derivative of this a minute, because this is what I'm going to have. du equals 2x dx, or du,
Derivative.
are you with me on this? Okay, now, I'm going to put a u up here, but then I want a u down here. Okay? So, what I'm going to make this, I'm going to change this reading to be dy dx. And this, what I circle here, is all of this stuff right here. You get, oh, hey, good. Okay? Because that's a little tricky first times we do things. Okay? Now, I know that this is equal to dy du, and you just have to kind of pull that out of your head. Du dx. Okay? Now, this here quantity right here, I'm going to write d du and then what y is equal, which is all of this. Now watch how I do this. I'm going to put 2 here, but instead of putting an x, I'm going to put what it's equal to, and I have a u. Okay? And then I have 1 over p squared dp, like this. Oh, okay, now I have not used this part yet, so I'm going to put that back here, and this is my little box over here, and that happens to be 2x. Okay? So, and Grant is our expert on this. I don't know, are you watching this, Grant, or not?
1x or 1u squared.
A 1u squared is what this turns out to be. Okay? And then we're going to have to put a 2x back here. Now we've got x's and u's around. I want all x's. So then I'm going to put it back in. It's 1 over x to the 4th times 2x. And which turns into 2 over x cubed. Now when you see this answer in the back, that's going to confuse you a little bit. If it be written this way, you maybe would have a better clue where it came from. Yes.
Do you have to do all that u junk, or can't you just, we know x squared equals p, so can't you just put your x squared in for the p's then? And
Okay, we listened to DeVries talk. Okay, hey guys, I'm serious. I'm just, I want to say what he's saying, because there's going to be a time where some of you are going to want to do this in other kinds of problems, and some of you won't be able to do this. You'll have to do it a longer process, which is no problem. Okay, now, Derek, you're going to do, you're just going to put
x squared in for p.
Okay, so you're going to have like this. Then what? Oh, this is the
And then dp, you just do derivative of p, which is derivative of x squared.
No,
It works.
no. He made a mistake, but got the right answer.
Well,
It is not due to this, it's due to this. And so I'm going to change the problem a little bit. Okay? If I put a 3 up here, it wouldn't work as well.
Why not?
That's what the problem
Okay,
is.
let's do it, and I will change all the things. I'll put a 3 up here like this.
Mm-hmm.
Okay, and so this has got to be 3 here, and so this turns into 3x squared dx. And so let's see, this turns into 3x squared like this. Now how am I coming along here? This is you work all right up to here. You with me all the way? Oh, just a second. Oh, no, we're okay. Okay? And now this becomes a 3x squared.
Mm-hmm.
And let me just have a little space at the bottom here. And so this turns into p, 1 over p squared. No, excuse me. 1 over u squared, because of what we do here. And then this becomes 3x squared like this.
Mm-hmm.
Okay, so this turns into
So it's still
1 over x to the 4th times 3x squared. So it turns out to be 3 over x squared.
no, it's 1 over x to the 6th.
Yeah.
Yeah, but you can still put p
Oh,
in.
hey, this is supposed to be to the 6th,
Yeah.
and so this is going to be to the 4th.
So it still
It
works.
still works.
Did that work too yet?
Yeah.
That's what you told us to do when you first told us how to do calculus. Yeah.
It works.
Say it once again, Derek, so I can listen.
You put x cubed, that top number, in for p. And then for dp, you just take the derivative of that number.
Much easier.
Okay, now why? Because it works. Okay, now here's the real reason. You are using, in a sense, the chain rule in reverse.
Yes.
And you're catching on to it.
Wonderful.
Now some of these people are catching on to it quicker now because they were in a session this morning where we talked for an hour. Okay? So, hey.
So can we do that?
No, I want this way. But after this, only if I ask you the question this way. Otherwise, do it that way.
Alright.
Okay? Yep.
Figured out for the test.
73. 73.
I'm like you.
You'll love it.
No, I won't.
I'll be done.
Who's dumb?
What about that one?
Can you explain why?
Well, at this point,
Because.
it says, determine the following statements that are true. Okay, suppose f is a positive increasing function. Okay, so here we go. Here it's a positive function and it's going up. Okay, okay, now. So you got that. And suppose f is a positive increasing, okay, got that. And x is greater than 0. We're over here. Okay? Then the area of that is an increasing function. Okay? Now this ties into that problem that Grant was asking a while ago. I don't have a third one. Okay? So we're going to be looking at the areas as we're going this direction.
I'm just going to keep getting bigger.
Yeah. That's what it said.
And then the other one, since it's getting smaller, it's going to keep getting.
I think so. Okay?
Question.
Yes.
Can you do that 53 now using that u? Well, now that was a different problem. But can you do it with the u?
Which one?
That 53 with the u. Using the u.
Shut up!
52?
No, 53.
Didn't I do that one already?
No, but you didn't do it with the u. Well, could you do it again, please?
No, you
should have paid attention there.
I was. My way worked.
Just watch the video. No, I'm gonna watch the video.
Yeah, we're not gonna
I'll figure it out. See, technically this is a different problem. You did x squared.
Yeah, I know.